Hi, my name is Antonio Velasquez. I was a student on Neuromatch Academy last year. I'm living in Guadalajara, Mexico, and I'm a biologist. I have worked on the fields of bioinformatics and electrophysiology for some time now. And right now we're going to go through what multiple linear regression is and what polynomial regression is. All right. So we may already know what a linear model is. The linear model is the same thing that we usually see in statistics 101. But right now we're going to talk about how to improve on those linear models. And the first thing will be on the number of features. All right. So the linear model or linear regression that you learn on statistics 101 might be nice if you only have one variable. But the thing is that on neuroscience, usually you want to model more than one neuron. So we're going to need way more features, right? So we're going to go through the tutorial real quick. First, we're going to do setup cells. All right. Okay. So here's the juice, the real math behind the process, all right? So we might define linear model as y equals theta of x plus an error term, theta meaning the slope of this model, all right? So we can express a multiple linear regression model as y of theta 0 plus theta 1 of x1, theta 2 of x2, and so on and so forth, plus an error term, all right? One question might be what this theta 0 means. Well, that's the intercept, all right? That's the intercept. That's real cool, all right? So we can express it as a sum, or we can express this as a matrix form, as is going to be equal to, y is going to be equal to a matrix multiplication, matrix x times theta plus the error term, all right? Where X is a matrix containing the feature value on columns, and for each row, the samples, right? So that's good to memorize. So features on the columns and samples on the rows, okay? So it's really easy to think about it instead of an infinite sum, right? So this is going to be how it looks like, right? This is going to be the matrix of data that we have and a vector of theta terms that we want to optimize. Okay. So we're going to simulate some data here. And these are a real example of what multidimensional features look like. Okay. This is the fancy expression for the optimization of theta values or theta parameter, theta hat. Okay. Well, here it looks complicated as an infinite sum as well through n. But again, we can express this as a matrix. All right. So these are real cool, and this is how I like to do it, and this is how the tutorial likes to do it as well. We're going to define the theta hat values as the multiplication of x transpose times x, both matrices, inverted, times the x transpose again, times y. All the multiplications here are matrix multiplications, all right? So we're going to go through the tutorial real quick. Okay, so we're going to use that formula, the formula above, to get to the answer. All right, first we're going to comment this. And here it tells us that we're going to use the point T to transpose the matrices and np_linlag.inf for the matrix inversion. All right, so inverting matrices is kind of complicated, so we're going to use this special function from NumPy. All right. X transpose. Remember matrix multiplications on NumPy. It's with this little symbol right here. Again, X, then matrix multiplication, X transpose, then matrix multiplication times Y. Okay, now we comment the results. All right, we get an error real quick. All right, simple error here with these. Okay, just going to copy it. Right, just to prevent any errors. And there you go. Same thing that we have right here. This is, okay, the output of this function is the vector theta hat or theta that we had right there. All right, so for 3 terms, for example, these are theta values. All right. So again, let's just do the error. The error here for the data simulated is around 0.91. All right. So the mean square error, that's real nice. So let's predict the results. And here we see a plane on the or the multidimensional data. And we can see the little errors here. So that's really cool. So that's how we start modeling for more than one dimension. And in neuroscience, that's really, really common. All right. So let's talk about polynomial regression real quick.